The next speaker is, so it will be a movie by Nuphar Gedulter and from Hebrew University, Jerusalem, and the title is Insights into Formation and Preservation of Biosignatures from the Study of Dead Sea Stromatolites.
Hello, everyone. I'm happy to introduce you my research about Dead Sea stromatolite reefs, hyperspectral remote sensing, and the search for life in extreme environments. First of all, I would like to explain what stromatolites are. They are laminated biosedimentary structures formed by sediment trapping and binding of microbially assisted mineral precipitation. They are generally created by the activity of photosynthetic and anaerobic microbial communities in shallow water environments. At the Dead Sea, these communities comprise halophiles, which are surviving under extremely arid environmental conditions. Here we can see a sample of a stromatolite from the Stromatolites dome, which we sampled at. These are stromatolite samples and sections. Stromatolites have unique features that can be detected by hyperspectral remote sensing techniques. And here in the photo is stromatolites from Western Australia. In order to understand the formation of ancient Dead Sea stromatolites, we also sampled modern microbial communities living in ponds supplied with fresh water at the Engedi shore. Our research focused on aragonite-forming microbial mats, which are more likely to build up on fossil stromatolites, such as these mats. According to the abundance of stromatolites in the geological record, in particular near the last glacial maximum, the Dead Sea area presented better conditions following the development of a microbial-rich environment. This is an orthophoto of a drone that we took. This layer is the stromatolites layer, and here is a neighboring layer, which we're calling a background layer. This is the site. So what are the advantages of mapping stromatolites? First of all, stromatolites represent some of the most ancient forms of life on Earth, dating back 3.5 billion years ago, and they're bearing information regarding the primitive conditions in which early life has appeared and evolved. And the quest to shed light on such processes on livable planets has been motivated thorough investigations of stromatolites, such as NASA's investigation with Perseverance rover conducting now. This is Martian photos compared with terrestrial photos. This is stromatolites from Lake Tethys, Australia. This is a concentric specimen from Mars, which resembling the concentric form. And these algae microbial mats from Earth compared with photos from Mars. Currently, the main practical attraction revolving around these stromatolite textures is their analogies with potential life and fossils on Mars. And I will examine fossil stromatolites in order to create a spectral classification for detection of their structures through spectral measurements. And I will examine the possibility to upscale the mapping using airborne and satellite imagery. First of all, using spectral classification through a spectrometer, followed by hypercam characterization and an XRF. And detection and mapping of the stromatolites will be conducted from PRISM hyperspectral satellite imaging, which is will also be conducted through ENVI software's classification tools. And the main challenge is that the surrounding rocks are carbonatic and originated from algae as well. Here we can see initial results from the spectrometer readings. On the left, stromatolites, on the right, the background. These measurements indicate the ability to distinguish stromatolites from their environment at SWIR wavelengths, which is here. In order to evaluate the differences between the two groups, I have divided the average hyperspectra, average of the spectrometers data from the slide before, of the background by that of the target, the stromatolites. And the absorption of principal constituents is inserted upon the spectra ratio line here. The machine learning model, I've used the gradient boosting classifier, which has successfully identified the stromatolites from the background by using the most indicative wavelengths. This is the most indicative one. The XRF readings, well, in attempt to find the most effective elements for a clear differentiation between the two groups, the ratio of strontium was found promising. This group in blue is the stromatolites. And the suggested explanation is that stromatolites are likely to contain a high aragonite concentration comparing to their environment. Strontium is likely to substitute calcium in aragonite minerals with its large cation. These are SEM photos of the microbial mats. Here we can see the EPS in the strings and the possibility of a diatom and spirulina living in the mats. These are the mats from the binocular photos. And to conclude, I seek a spectral signature of stromatolites, which should eventually lead to automated mapping through remote sensing images. I'm examining fossil stromatolites in order to create a spectral classification for detection of their structures through spectral measurements, and will examine the possibility to upscale the mapping using airborne and satellite imagery. The correspondence between the spectral ratio and the machine learning model enhances the overall possibility of the model to predict the differences between the two groups. And my research used integration of hyperspectral remote sensing methods with machine learning, which is a rather new take, and an attempt to produce a significant classification and detection over vast data. Developing techniques of remote sensing for automated mapping can ultimately achieve the greater aim of finding traces of life on Mars or other planets. Thank you.